On one side, Brian Josephson is a figure of pure, crystalline intellect, a Welsh theoretical physicist who, at the age of just 22, made a discovery hidden deep within the strange mathematics of the quantum world. A graduate student so assured of his calculations that he stood up in a crowded London conference hall and publicly interrupted a two-time Nobel-winning physicist in the 20th century to correct him. His insight was so groundbreaking that it earned him the Nobel Prize in Physics at the age of 33, making him one of the youngest physicists ever to win a Nobel in physics, and etching his name into the bedrock of the field with the Josephson effect, a phenomenon that revealed a deeper layer of quantum reality. He is the scientist's scientist, a mind of uncompromising rigor. But there is another side of him, one where the first one seems to end. This Brian Josephson is an emeritus professor at Cambridge, but he now speaks a different language. He attends conferences not to discuss superconductivity, but to defend research into telepathy, psychokinesis, and other paranormal themes. He speaks of Eastern mysticism, the intelligence of nature, and a grand mind-matter unification project. To many of his peers, he is a cautionary tale, a brilliant mind lost to the siren song of the fringe. Quantum physicist David Deutsch once described his claims as utter rubbish. Others have labeled him a voodoo scientist. How can these two men be the same person? The easy answer is that they are not, that something changed, that the peerless mind that solved one of the great puzzles of condensed matter physics later realized something different. But that is the easy answer, and it may be the wrong one. His shift in priorities and focus was not a sharp break, but a transition. The same mind that allowed him to see an impossible current flowing through a solid barrier of semiconductors is what later drove him to look for consciousness in the fabric of the cosmos. His career is not a story of a scientist who abandoned his field, but of one who tried to expand its borders beyond what the existing maps would allow. The story begins in Cardiff, Wales, where Brian David Josephson was born on January 4, 1940. From an early age, his intellect was apparent. At Cardiff High School, his physics master, Amrus Jones, did more than teach the standard curriculum. He opened a door for the young Josephson into the abstract and beautiful world of theoretical physics, a place of pure thought where the universe's rules could be explored with mathematics alone. When he arrived at Trinity College, Cambridge in 1957, it was to study mathematics. Cambridge was the home of Newton, Maxwell, and Dirac, a place where the mathematical architecture of reality was revered. Yet after 2 years, Josephson grew restless. He found the world of pure mathematics somewhat sterile. The intricate logic was not enough. He needed it to connect to something tangible, to the messy physical world. He switched to physics. It was a move that defined his intellectual character. He was a mind driven not just by abstract perfection, but by the desire to see that perfection manifest in reality. He was known as a brilliant but shy student, a quiet presence in the lecture halls, but his quietness concealed a mind of formidable and exacting standards. His professors soon learned that to lecture in front of Brian Josephson was to submit one's own understanding to the most rigorous of tests. One of his former lecturers recalled the distinct need for precision in any presentation given to a class that included Josephson. If the lecturer made a mistake, however small, Josephson would not let it stand. After the class was over, he would politely confront the instructor and explain the error. Philip Anderson, a future Nobel laureate himself, who was a visiting professor at Cambridge in 1961, had a similar experience. He later recalled that having the young Josephson in a class was a disconcerting experience for a lecturer. I can assure you, because everything had to be right or he would come up and explain it to me after class, Anderson said. These were not the actions of any arrogant mind seeking to show up. They were the reflexes of a mind that was fundamentally uncomfortable with error. For Josephson, a logical inconsistency or a factual mistake was not a trivial matter. It was a disruption in the order of things that had to be corrected. This absolute demand for intellectual correctness was the engine of his genius. It was this quality that would soon lead him to a discovery that would challenge arguably the world's most respected physicist at the time. And it may be this same quality that later led him to challenge the very foundations of science itself. A mind that cannot tolerate a small error in a lecture is a mind that will eventually be forced to confront the largest gaps in human understanding, such as the nature of consciousness, rather than simply accepting them as mysteries beyond reach. In 1962, the world of physics was still absorbing the implications of a radical new understanding of superconductivity, the strange state where certain materials, cooled to near absolute zero, lose all electrical resistance. The theory, developed by John Bardeen, Leon Cooper, and Robert Schrieffer, BCS theory, explained this by proposing that electrons, which normally repel each other, could form pairs that moved in perfect lockstep, creating a collective quantum state that flowed without friction. Into this world stepped Brian Josephson, a 22-year-old PhD student who had just been elected a Fellow of Trinity College. He had been attending Philip Anderson's lectures on a concept called broken symmetry. Josephson became fascinated by a subtle but consequential feature of the theory. The macroscopic quantum state of a superconductor had a property called phase. He wondered if this theoretical mathematical property could be made real, if it could be observed in an experiment. He considered a hypothetical setup: two superconductors separated by a vanishingly thin insulating layer, a barrier that, according to classical physics, no current should be able to cross. But quantum mechanics allowed for a bizarre phenomenon called tunneling, where a particle could pass through a barrier it did not have the energy to overcome. Josephson began to calculate what would happen to the electron pairs at such a junction. His mathematics led him to a conclusion that was both elegant and shocking. He predicted two effects. First, a supercurrent of paired electrons could flow across the insulating barrier with no voltage applied at all. It was as if the two separate pieces of metal were acting as a single, coherent quantum object, connected by the invisible property of phase. Second, if a voltage was applied across the barrier, the current would stop its steady flow and instead begin to oscillate back and forth at an extremely high and precise frequency, directly proportional to the voltage. The idea was so strange that even Josephson was initially dubious. His own thesis advisor, Brian Pippard, was skeptical. Pippard argued that the probability of two electrons tunneling simultaneously to form a pair on the other side would be infinitesimally small, making any such effect unobservable. But Josephson trusted his calculations. He wrote up his findings in a paper titled Possible New Effects in Superconductive Tunneling, which was published in the new journal Physics Letters on July 1, 1962. As established journals will likely find the idea too radical. The paper might have vanished into obscurity, but it caught the attention of the one man whose opinion mattered more than any other: John Bardeen. Bardeen was a giant of physics. He was the co-inventor of the transistor, a discovery that had already won him a Nobel Prize in 1956. He was also the B in the BCS theory, the world's foremost authority on superconductivity. Bardeen read Josephson's paper and dismissed it. His intuition, grounded in the physics he had helped create, told him it was wrong. He believed that the electron pairing responsible for creating superconductivity could not extend into the insulating barrier itself. If there were no pairs in the barrier, there could be no flow of paired current across it. On July 25, 1962, just weeks after Josephson's paper appeared, Bardeen submitted a rebuttal to the prestigious journal Physical Review Letters. His conclusion was blunt and absolute. There can be no such superfluid flow. The case, it seemed, was closed. The world's leading expert had declared the student's idea impossible. The dispute came to a head 2 months later, in September 1962, at the 8th International Conference on Low-Temperature Physics, held at Queen Mary College in London. The confrontation has since become a legend in the history of physics, a battle between mathematics versus intuition, between radical ideas versus convention. When Bardeen, then one of the most eminent physicists in the world at the time, began speaking, Josephson, who was still just another student, stood up and interrupted him. After an intense debate, both men were unable to reach a common understanding, and at points Josephson repeatedly asked Bardeen, "Did you calculate it?" "No, I did." The public confrontation forced the physics community to take the students' impossible idea seriously. The final verdict, as always in science, would come from an experiment. At Bell Labs in Princeton, Philip Anderson, the same physicist whose lectures had first inspired Josephson, urged his colleague John Rowell to try to find the effect. In January 1963, they succeeded. They submitted a paper to Physical Review Letters titled "Probable Observation of the Josephson Superconducting Tunneling Effect." The impossible was real. The confirmation opened the floodgates. Josephson's discovery led to the invention of SQUIDs, or superconducting quantum interference devices, instruments of astonishing sensitivity used in medicine and geology. It provided a new, powerful confirmation of the BCS theory and raised metrology to a new level of precision. The discovery came to be known as Josephson effect. A cascade of awards followed for the young physicist. In 1970, he was elected a Fellow of the Royal Society at the age of just 30. In 1972, he received the Hughes Medal. The journey culminated in 1973 when Brian Josephson shared the Nobel Prize in Physics with Leo Esaki and Ivar Giver for their work on quantum tunneling. He was awarded half the prize specifically for his theoretical predictions of the properties of a supercurrent through a tunnel barrier. He was just 33 years old. The confrontation with Bardeen was more than just a victory. It was a formative experience. It had proven to Josephson that he could be right when the entire establishment was wrong. He had learned from direct experience that being an outsider, even being publicly rebuked by a titan, did not mean he was incorrect. It was a lesson that would embolden him for the far greater intellectual battles that lay ahead. For many scientists, the Nobel Prize is a capstone, the ultimate recognition of a life's work. For Brian Josephson, it was a key. In a later interview, he explained that the prize gave him a bit more freedom to work on my interests, which are on the unconventional side, without people feeling that they can say, "You can't work on that." He had already begun to feel, in the late 1960s, that mainstream physics was passing through a less interesting period. The revolutionary excitement of the early quantum era had faded, replaced by more incremental work. He began to look elsewhere for the truly fundamental questions. The biggest and most compelling problem he saw was not in the behavior of cooled metals, but in the nature of the human brain and consciousness itself. His journey took him into a new direction. In 1971, 2 years before receiving the Nobel, he began practicing transcendental meditation, or TM. He became a visiting faculty member at the Maharishi European Research University in the Netherlands, a central institution of the TM movement. He was drawn to the ideas circulating in the intellectual counterculture of the time. He read Fritjof Capra's influential 1975 book, The Tao of Physics, which argued for deep parallels between the concepts of modern physics, like entanglement and the observer effect, and the insights of Eastern mysticism. Eastern mysticism encompasses spiritual traditions from Asia, such as Hinduism, Buddhism, and Taoism. It focuses on achieving personal enlightenment through practices such as meditation, karma, and the interconnectedness of all life. Josephson began to sense that the puzzles at the heart of quantum mechanics were pointing toward a deeper connection between the physical world and the mental world of the observer. He later stated, "I began to sense that conventional science is inadequate for situations where the mind is involved, and the task of clarification became a major concern of mine." Around this time, across the Atlantic, in Berkeley, California, a similar intellectual restlessness was taking hold. In May 1975, a circle of young physicists formed the Fundamental Physics Group. They were a generation trained during the post-Sputnik boom, who graduated into a crashed job market, leaving them with time and inclination to question the orthodoxy. They were frustrated with the shut up and calculate mentality that had come to dominate physics after the Manhattan Project. Like Josephson, they wanted to return to the big philosophical questions that had animated the founders of quantum theory, such as Bohr, Heisenberg, and Schrödinger. They dove into the strangest corners of the field: Bell's theorem, quantum entanglement, and the measurement problem. And, like Josephson, their explorations led them to quantum mysticism and parapsychology. This group of hippie physicists became local celebrities, their work even attracting the interest of the CIA and DIA, which funded experiments into remote viewing at the Stanford Research Institute, with the Fundamental Physics Group acting as house theorists. Back at Cambridge, Josephson sought to formalize his new intellectual pursuit. He used the freedom his Nobel afforded him to establish the Mind-Matter Unification Project within the prestigious Cavendish Laboratory. Its stated goals were ambitious, even audacious, to explore the idea of intelligence in nature, to understand the relationship between quantum mechanics and consciousness, and to pursue a synthesis of science and Eastern mysticism. To his colleagues, it may have looked like he was abandoning physics, but in his own mind, he was pursuing its most fundamental questions. He was not leaving the path of physics. He believed he was following it to its ultimate, logical conclusion. The reaction from the scientific community was not long in coming. At science conferences, Josephson would often steer conversations toward meditation and telepathy, which irritated his colleagues. As his advocacy for unorthodox ideas grew more vocal, the irritation hardened into outright condemnation. He became a vocal supporter of a range of topics considered fringe by the mainstream. parapsychology or the study of paranormal phenomena, the possibility of cold fusion, and the controversial idea that water can retain a memory of substances dissolved in it. The denunciations became sharp and public. Fellow quantum physicist David Deutsch dismissed his claims as utter rubbish. He was shunned by many former colleagues, his name sometimes invoked as a warning against straying too far from the accepted path. In 2010, organizers of a conference on quantum physics withdrew their invitation to him, only to reinstate it after several other prominent attendees protested. His very presence had become a point of contention, a challenge to the boundaries of respectable scientific discourse. Josephson has never shied away from this conflict. He has a name for the scientific community's attitude: pathological disbelief. He argues that most physicists have an emotional response when they hear anything connected with parapsychology, and that their rejection is based not on a rational evaluation of evidence, but on a dogmatic belief that all research in this field is false. He compares the current dismissal of parapsychology to the decades-long resistance by geologists to Alfred Wegener's theory of continental drift. Wegener had strong observational evidence, but his proposed mechanism was deemed impossible by the leading physicists of his day. The establishment was wrong. His critique of the scientific establishment has only sharpened with time. In a June 2024 interview, he pushed back against the charge that his ideas are unscientific, arguing that some aspects of conventional physics are just as speculative. He described modern theoretical physics with its reliance on postulating unknown symmetries and extra dimensions as just as theological, as his own attempts to understand the universe through the lens of consciousness. He argues that we have direct knowledge of the mind's capabilities, its ability to create music, perform logic, and do mathematics, and that these known abilities provide a more solid foundation for a theory of reality than the purely mathematical abstractions of string theory. Today, Brian Josephson is an emeritus professor at Cambridge, still working from the Cavendish Laboratory, still directing his Mind-Matter Unification Project. He remains an active and defiant voice, a Nobel laureate who believes his most important work came after he won the prize. Ultimately, my work on the brain is more significant than my Nobel Prize-winning research, he has said, outlining what he wants his legacy to be.